In stats, we learned how to do a residual plot and talk about R squared and the standard deviation of residuals. So first off, I typed all this in my calculator. Yet again, we've been working on this problem for quite a while. And then Tuesday, we learned how to find a residual. You go y minus y hat. And that gives you one residual for one observation. But for this Gessel score data, there are 21 observations. So there are 21 residuals. You take each score, subtract the predicted, and you have a residual. And so you can make a graph of the thing. So we're going to make one here. I don't want y'all to stress out about making a residual plot. We're going to make one so we have one to talk about. But typically one is just printed for you on a test, and you need to know how to talk about it. So let's see if we can get one to show up on our calculator. When you type in all your data and you run linear regression, it's going to store these in a list in your calculator. These are stored somewhere. You just need to know how to pull them up. You don't have to read through all those. If you want to print them right here, highlight the top of an empty column, press var, then press link to, and look for the option that says stat resid, and it is right here. And there are all the residuals. Doing this is an easy way to cheat at getting a residual. You're not showing your work, which you do need to do, but you can know if you did it right. So like the 12th observation has a negative 3.7 residual. This kiddo that was 9 months old when he spoke had a Gessel score at 96. His residual was that right there. But let's pull up the graph. So you got to go to your home screen. You open up a graph. Your x needs to be, your x-axis needs to be the x variable, so age. And then your y-axis is your residuals. And you're ready to go. That's your residual plot. Interestingly, if you don't see a pattern, we're going to say that's a linear relationship. I don't see a pattern. Don't look at it too long or you'll start to create a pattern in your head. But I don't see a pattern there. This shows a linear relationship. What's happening here? Well, let's go back to the scatter plot. Here's our scatter plot. We made that earlier this week. And here's our least squares line. That's kind of rough, but let's imagine I did it really specific, and there it is. So if I take that line and I make it perfectly horizontal, so I literally grab it, turn it sideways, make it flat, and each of these distances here, these are all residuals. And that's what we see when I click residuals for the y-axis. It turns it sideways, and we have a residual plot. So in your notes, I would just do a rough sketch. So I'm going off of memory here. We had a residual plot that looked like this. And by the way, this line right here is the least squares line. And each dot, that's how far it is from the predicted line. So I did a rough sketch earlier. It looked something like this. This is like a sketch of a sketch, so chances are I'm a little off. You don't have to do a great job because, like I said, they're going to print this for you. I would not stress out over this. You just need to know how to read it. All right. So there's our residual plot. I would say there is no pattern in the residual plot. Therefore, a linear model is appropriate. Remember, we're zooming in on our scatter plot, turning the line sideways. If I want to say there's a linear relationship in the residual plot, there should be no pattern. All right? And I talk about it below this. So down here, let's actually change I don't know why I use that terminology down there. Let's say random scatter. Or you could say no pattern. That was kind of an oxymoron, wasn't it? Random pattern? Let's say random scatter. Or just no pattern implies a linear relationship. A pattern implies no linear relationship. So, for example, let's look at an example of a scatter plot and a residual plot. So right here, this first one, let's let it be a scatter plot. And let's let the second one be a residual plot. Let's say our graph looks something like this on the scatter plot. That one has a curving pattern to it. And the least squares line probably does something like this right here. So when I go to make my residual plot, it's just going to further prove that a linear relationship is bad. So you turn that black line sideways. And when I make my residual plot, remember it's the distances from the line, I'm going to have a graph that looks kind of like this. This has a pattern, even worse, a curving pattern. Back up. No linear relationship. This one right here, let's go back to green. So maybe I have, let's do a negative. So maybe that's my scatter plot as I read it left to right. It is dropping. And whenever I make my residual plot, I have random scatter. So this one is the scatter plot. And this one is the residual plot. What if you have this weird thing called a fan-shaped pattern? Well, one, it's a pattern, so that's a bad sign. Let's say poor linear relationship. Like, there's something going on here. A linear relationship might tell part of the story, but it's just going to do a bad job at predicting. Maybe add that. Does a bad job at predicting. So let's look at some examples. I may have a fan-shaped pattern that starts out all over the place. This is good. You know, we have random scatter. But you notice as you read left to right, it's narrowing. That's bad. That's a fan-shaped pattern. Or vice versa. Starts out really narrow, maybe, and then it spreads out. That would be really bad too. So those two are fan-shaped patterns. There's just more going on. You want to stay away from the words of no linear relationship, because there might be something linearly happening, but there's just something else going on there, and it's just a bad one. All right? I hope that makes sense. We did one more thing. We talked about these two other things. You've seen r squared at the bottom of the screen before. It's outputted on the calculator, but we've never even talked about standard deviation of the residuals. So what the standard deviation of residuals is it takes, trying to find my residual plot, it takes every one of these distances, this is the residual plot, and it finds the standard deviation of all those distances. So you have a bunch, you have 21 of them. All right? So what you need to be aware of is you don't have to calculate it. You need to know how to interpret it. So we'll practice that. That's on the next problem. I actually don't think we're going to get to it in this video. So in the next video, I will give it a shot, or I'll explain it. But it's on average how far the values are from the predicted value, from the predicted y. All right. But coefficient of determination, I will do that right here. One reason I'm not doing standard deviation of residuals yet is because we don't know what they are for Gessel score data. Usually they are given to you. I mean, we could find them if we wanted to, but I'm not worried about it. We'll practice it in the next example. So for the Gessel score data, we had an output in our calculator of 0.40997. That was r squared. It's also called the coefficient of determination. The phrase we need to absolutely for sure use is variation in y when we explain this. So yes, it is the square of r. Don't forget, r is correlation. It's the strength between x and y. All right, don't forget that. But when you square it, this is almost like a grade, like a square, a grade or a score of how good of a job the line is doing at explaining x and y. All right, so as these dots are like bouncing all over the line, the predicted line, it's like a grade of how good of a job the line does. So for the Gessel score, I would say 41.0%. Typically, I'd round further out, but that 799, it causes us to round up to 41.0. I mean, you could say that whole 40.997% of the variation in Gessel's score is explained by a linear relationship with age. So make sure if you're doing a multiple choice problem, you're picking the right interpretation. It has to have the phrase variation in y. It's not going to say y, it's going to say the y context. So Gessel score. These words kind of vary. Sometimes they say attributed to a linear relationship with age. Sometimes they'll skip the word linear and it's very brief. Attributed to a relationship with age and score. Sometimes they'll say the y variable again. But the boxed thing, this thing right here, is always, always there in a multiple choice problem. They'll throw you a curveball, they'll try and say variation in x, but that's wrong. All right. I didn't say it before, but r squared can be anywhere from 0 to 1.0 or 0% to 100%. And that's about it. So we'll practice this in an FRQ on Monday. Bye, y'all.